Section: Introduction. In this section, we explore the impressive capabilities of language models in areas like coding and mathematics. We recognize that many tasks, such as language modeling, are complex and can be broken down into simpler skills. The way these skills are learned is fascinating and can vary significantly. Some skills may be fully learned, partially learned, or not learned at all. Even among the skills that are learned, their progress can take different forms, such as sudden improvements, gradual growth, or fluctuating patterns. Despite observing these varied behaviors in experiments, our understanding of them remains limited. We believe that developing an intuitive understanding can help connect theoretical concepts with practical applications. To gain insight into skill learning, we adopt a physicist's approach of simplifying and abstracting complex subjects. For instance, when studying a cow in the wild, physicists make assumptions to simplify their analysis. This balance between science and art is crucial, as Einstein noted that we should strive for simplicity without oversimplifying. We propose three models that balance realism and simplicity: the geometry model, the resource model, and the domino model. Each model captures different aspects of skill dynamics. We use the terms skill and task interchangeably, defining a skill as the ability to perform a task. To motivate our discussion, we introduce the domino effect, which illustrates that skills often learn in a sequence, with some skills beginning to learn right after others have finished. For example, when we train two independent tasks with different frequencies, we observe that the second task starts to progress quickly only after the first task is completed. This suggests that learning task 2 takes significantly less time than expected due to the influence of the first task. We aim to understand the mechanisms behind the domino effect, starting with the geometry model, which allows for this effect to occur. We then develop a resource interpretation of the geometry model, leading us to the resource model, which describes how skills compete for limited resources. When tasks have a strong hierarchical structure, we can simplify the resource model to the domino model, where skills are learned in a strict order. While our initial focus is on the domino effect, these models have broader applications. The geometry model offers insights into neural scaling laws and optimization. The resource model helps us understand the dynamics of compositional tasks, and the domino model provides a framework for analyzing modularity. In the organization of our paper, we present models of varying complexities to explain the domino effect. These models are not only conceptually intriguing but also practically useful, with applications in various sections of our work. We begin by discussing our philosophical approach, leading to the geometry model, followed by an analysis of its behavior, a resource interpretation, and a study of both the geometry and resource models in different contexts. Finally, we simplify the resource model to the domino model, assuming a strong hierarchy of tasks. In summary, we aim to create models that illustrate the domino effect, starting with our philosophical foundation and progressing through our proposed models. Section Summary. In this section, we explore the learning dynamics of skills in language models, noting that skills can be learned in various ways and can influence each other sequentially, exemplified by the domino effect. We propose three models: the geometry model, the resource model, and the domino model, to capture these dynamics, emphasizing the importance of simplifying complex phenomena while retaining their essential characteristics. Section: Introducing the geometry model. In this section, we introduce the geometry model, which focuses on skill dynamics and loss evolution. We make two key assumptions. First, that tasks are independent, meaning the total loss is an average based on how often each task occurs. Second, we assume a linear representation of tasks, where skill levels depend on their alignment with specific task vectors. While the independence assumption may not be entirely realistic, we adopt it for simplicity and plan to address it later when examining task composition. The linear representation aligns with recent findings in task arithmetic. We simplify the geometry model by specifying task vectors, which we assume are randomly selected from a Gaussian distribution. We consider a model overparameterized if the number of tasks is less than or equal to the number of dimensions. Otherwise, it is underparameterized. In the overparameterized case, we make the task vectors orthogonal, which simplifies our understanding since moving along one task vector does not affect others. In the underparameterized case, we cannot achieve orthogonality, leading to skill correlation, a fascinating aspect of large language models today. Next, we typically use a power law distribution for task frequencies, where a larger exponent results in a more skewed distribution. We then train the geometry model to observe interesting skill dynamics, such as the domino effect, using optimizers like SGD, SignGD, and Atom. We start with a simple two-task setup, where tasks have defined frequencies. We use a squared error loss function to mimic regression and randomly generate task vectors, ensuring they are orthogonal and normalized. We train the model with 3 optimizers and test various weight combinations. We find that the convergence time for the second task is sensitive to its frequency, while SignGD shows a consistent delay regardless of frequency. Atom's performance is intermediate. We are particularly intrigued by the constant delay from SignGD, where the second skill only progresses after the first skill has finished learning, illustrating the domino effect. We interpret this effect through resource competition. Even though skill vectors are orthogonal, they can still interfere during optimization. For instance, in SignGD, if one skill's gradient is much larger, it dominates the update direction, delaying progress on the other skill until the first skill's gradient diminishes. In contrast, SGD allows both gradients to contribute without interference. To quantify this, we track the number of dimensions aligned with each skill's gradient during training. We observe that as one skill's alignment decreases, the other's increases, suggesting a conservation of learning resources. This resource interpretation inspires our proposed resource model. Finally, we extend our analysis to multiple tasks with a power law distribution and examine different exponents and task counts. We find that skills are learned sequentially based on their frequencies, but we still seek to understand the quantitative aspects of these dynamics, particularly the conditions under which the domino effect occurs. This leads us to propose the resource model for further exploration. Section Summary. In this section, we introduce the geometry model, which makes 2 key assumptions. Tasks are independent and linearly represented by model parameters, allowing us to analyze skill dynamics and loss evolution. We explore the effects of task frequency and optimization methods on learning, particularly noting the domino effect, where progress in one skill can delay learning in another, and we propose a resource interpretation to explain these dynamics. Section. Introducing the resource model. In this section, we introduce a resource model that interprets the dimensions aligned with gradients. We observe that when resources increase for one task, they typically decrease for others, indicating that the number of model parameters acts like a resource pool allocated to various tasks. Based on this idea, we propose a resource model. We note that a specific constant factor is derived by aligning the geometry model with the resource model in a single task scenario. At the beginning, all tasks start with equal resources, and the distribution of resources is determined by the data. The only adjustable parameter in our resource model is denoted as N0. Once we set N0, we can numerically solve the ordinary differential equation. N0 represents the proportion of resources that are wasted. Our findings show that a smaller N0 results in faster learning, while a larger N0 slows it down. We can adjust N0 to align the skill dynamics of the resource model with those of the geometry model. Although the geometry model includes many specific details, these can be effectively summarized by the parameter N0. To test the resource model with different hyperparameters, we modify optimizer settings and find that there is always a corresponding N0 that produces similar skill dynamics to the geometry model. Interestingly, changing the data distribution does not affect N0, suggesting it is primarily influenced by optimization details. We also discover that reducing the learning rate leads to a smaller N0, as it minimizes fluctuations in already learned skills. Conversely, increasing noise or reducing batch sizes raises N0. Adjusting the parameters of the atom optimizer can also change N0. We also highlight a valuable analytical property of our equations. There are conserved quantities within the system. Specifically, we find that the ratios of certain variables remain constant, indicating that learning curves should align when adjusted by their frequency. We confirm this behavior numerically for the resource model and approximately for the geometry model. Now, we need to determine the variable c, which relates to the learning time. By substituting c back into our equations, we can express the time it takes to reduce c from 1 to a lower value. This time consists of two components, the time spent on tasks and the time wasted. The total time spent on tasks is proportional to the number of tasks, while the wasted time is linked to the resources that are not effectively used. Lastly, we note that N0 increases with the learning rate, provided the learning rate is not too small. This relationship suggests that the optimal learning rate, which maximizes the effectiveness of our equations, decreases over time. This observation supports the common practice of learning rate decay in machine learning. In large language models, it appears that N0 grows faster than linearly, reinforcing the need for learning rate adjustments. Section Summary. In this section, we introduce a resource model that interprets model parameters as a resource pool allocated to tasks, where the parameter n_0 represents wasted resources and influences learning dynamics. We find that n_0 can be tuned to align the skill dynamics of the resource model with those of the geometry model, and it is affected by factors such as learning rate and noise, while also revealing conserved quantities that relate learning curves across tasks. Section: The Underparameterized Regime. In this section, we explore the underparameterized regime of language models. The idea behind the notion that scaling is all you need is based on the belief that even though current large language models have billions of parameters, they still struggle with complex language tasks. This indicates that we are still underparameterized for effective language modeling. In this regime, not all skills can be learned, and skill interference occurs because we cannot have enough distinct task vectors in a space that is too small. To investigate the underparameterized regime using the geometry model, we simply need to ensure that the number of tasks exceeds the number of dimensions. Each task vector is a unit vector pointing in a random direction. The inner product of two task vectors tells us if they work together, positive inner product, or compete, negative inner product. We analyze both regression, using squared loss, and classification, using cross-entropy loss. We set the number of dimensions to 10 and vary the number of tasks from 5 to 100. We utilize the Sign-GD optimizer with a specific learning rate and batch size. Our findings show that as the number of tasks increases, some tasks may not be learnable or may perform worse than random guessing due to negative correlations with stronger skills. These correlations lead to complex dynamics that differ from those seen in overparameterized models. For the resource model, we need to account for correlations between different skills. We can use the inner products from the geometry model to define a correlation matrix. This matrix helps us understand how skills relate to one another. In the overparameterized regime, the correlation matrix had all off-diagonal terms as 0, but now we present a more general model that captures these correlations. In the regression setup, we see that correlations from other skills influence the learning process. When the correlation matrix is an identity matrix, our equations simplify. The skill dynamics align well with the geometry model. In the classification setup, we focus on next token prediction, which is more realistic for language modeling. We can replace certain terms with gradients from the cross-entropy loss, and the resulting skill dynamics also match the geometry model, capturing the nonlinear learning dynamics. Next, we introduce the Domino model without extensive justification. We show that this model can be derived from the resource model as a special case. To simplify our equations, we make two assumptions. First, that there is no waste in learning, and second, that there is a strong hierarchy among skills. With these assumptions, we find that the first skill is learned at a constant rate, and once it is mastered, the second skill takes over, continuing this pattern until all skills are learned. This sequential learning process resembles falling dominoes, hence the name, domino model. In practice, the model may only learn a subset of tasks, and the learning time for all tasks scales linearly with the number of tasks, which is consistent with the resource model. However, we will explore ways to reduce this learning time from linear to a square root of the number of tasks by utilizing modularity in future sections. Section Summary. In this section, we explore the underparameterized regime of language models, highlighting that as the number of tasks increases, some tasks may not be learned effectively due to skill interference. We introduce the domino model, which simplifies the learning process by assuming a sequential learning order, where each skill is learned one after the other, and we discuss how this model can potentially reduce learning time from linear to sublinear with modularity. Section. Implications for neural scaling laws. In this section, we explore the implications of neural scaling laws, which describe how model performance improves as we increase resources like data, parameters, and computing power. We aim to understand the underlying mechanisms of these laws, particularly how two exponents, alpha_n and alpha_s, relate to another exponent, alpha, which defines the data distribution. We begin by revisiting the quanta model, which suggests that network knowledge is divided into discrete units called quanta. This model accurately predicts alpha_n but tends to underestimate alpha_s. According to the quanta model, each task requires a fixed number of parameters, allowing us to determine how many tasks a network can learn based on its parameters. The loss function, when considering unlearned tasks, leads us to find that alpha_n equals alpha-1. The domino model shares a similar premise, predicting the same relationship for alpha_n. For alpha_s, the quanta model posits that the time to learn a task is inversely related to the task's probability, leading to a specific relationship between the number of steps and the loss. However, this relationship holds true primarily when using stochastic gradient descent, SGD, as the optimizer. When we use adaptive optimizers like SignGD, the domino model suggests a different relationship for learning time, resulting in a different prediction for alpha_s. We note that for alpha greater than 1, the quanta model predicts that alpha_n is greater than alpha_s, while the domino model suggests they are equal. This aligns with some published results, although we do not claim that the domino model fully captures scaling behavior. It can, however, be useful for incorporating the effects of adaptive optimizers. Next, we introduce the geometry model, which assumes that skills are independent but acknowledges potential correlations among task vectors. We conduct experiments with various dimensions and data distributions, training the geometry models using different optimizers. For alpha_n, we find that the loss behaves as a power law in relation to the number of parameters, and the geometry model consistently predicts a larger alpha_n than the quanta model. Notably, for alpha equal to 1, the geometry model aligns with observed scaling exponents, while the quanta and domino models do not. We also observe a critical point in the loss function as we increase the number of parameters, indicating that the model can learn all skills when the number of parameters meets or exceeds the number of tasks. However, we believe that this critical phenomenon may not be observable in current large language models, as they likely remain underparametrized. For alpha_s, we find that the loss is a power law of training steps. Our results show that the geometry model with SignGD aligns with the predictions of the domino model, especially for larger alpha values. We also note that using Atom as an optimizer results in smaller alpha_s values compared to SignGD, highlighting the significant impact of optimization methods on scaling behavior. Lastly, we confirm that the quanta model consistently underestimates alpha_s. Section Summary. In this section, we explore neural scaling laws, focusing on how the quanta and domino models predict the scaling exponents alpha_n and alpha_s based on resource allocation and learning dynamics. We find that the geometry model provides more accurate predictions for these exponents, particularly for alpha equals 1, and highlights the significant impact of optimization methods on scaling behavior. Section: Multitask Sparse Parity. In this section, we conduct experiments using real neural networks on the multitask sparse parity task. This task involves binary classification of binary strings. The input consists of a combination of bits from multiple subtasks and an additional parameter that influences the complexity of these subtasks. For each subtask, we randomly select a subset of bits from the trailing part of the input. In any given input, only one of the initial bits is set to 1, while the others are 0. The label for the input string is determined by the parity of the selected subset of bits. The trailing bits are chosen randomly. Our network needs to learn how to compute the parity from the correct subset of these trailing bits. We apply a power law distribution to the occurrence of the various skills, meaning the chance of a specific bit being 1 decreases with its index. We train our models using ReLU multi-layer perceptrons with a single hidden layer, setting specific parameters for the number of tasks, bits, and batch size. In our results, we explore different configurations of the Atom optimizer, adjusting its parameters. We observe that the scaling behavior of our models varies depending on the optimizer used, which was not previously noted. For example, with certain parameter settings, we find a lower scaling exponent compared to the default settings. This highlights the significance of optimization choices in analyzing scaling laws. However, we do not find a precise relationship between the scaling exponents for the different tasks and the overall model performance. We also consider the implications of our findings for optimization. We note that different optimizers can lead to varied training dynamics, raising the question of whether these insights can be applied to real-world training scenarios. If so, we could speed up the process of idea iteration, allowing for quicker experimentation with simpler models. Next, we introduce a straightforward quadratic loss function that illustrates the domino effect. We show that this loss function can reveal the domino effect in a simplified manner. We define our parameters and their relationships, noting that when the loss is aligned with the basis, all sub-losses decrease uniformly. In contrast, when the loss is not aligned, we observe a domino effect where one sub-loss only decreases after the previous one has reached near 0. Section Summary. In this section, we explore the multitask sparse parity problem, a binary classification task where neural networks learn to compute the parity of selected bits from binary strings. Our experiments reveal that different configurations of the Atom optimizer significantly affect training dynamics and scaling laws, highlighting the importance of optimization strategies in achieving efficient model training. Section: Grokking. In this section, we discuss grokking, which is when generalization occurs long after memorization. We notice that the learning process includes a quick phase of overfitting followed by a slower transition to generalization. Most studies on grokking utilize the Atom optimizer due to its popularity in machine learning. However, we found that SignGD can outperform Atom in certain cases, prompting us to explore its performance in the grokking context. We set up our problem based on the work of Power et al., who observed grokking in learning binary operations. We focus on the modular addition problem, where we represent each number as a 32-dimensional embedding vector. A 3-layer neural network processes these embeddings and outputs class logits. We split our data into training and testing sets and train the model using either Atom or SignGD for 10,000 steps, with and without weight decay. Interestingly, SignGD is a specific case of Atom, differing mainly in its parameters. Our results show that SignGD achieves better and faster generalization compared to Atom. Without weight decay, SignGD reaches about 90% test accuracy, while Atom struggles to achieve any accuracy. With weight decay, SignGD still generalizes more quickly. We believe that Sign's advantage comes from its smaller parameter controlling the decay rate, which allows for faster learning. We also explore data reweighting, noting that less frequent skills are learned later in training, especially when the parameter controlling this effect is large. We propose that when the network encounters a less frequent skill, we should assign it a larger weight to balance its rarity. However, implementing this idea is challenging, as we cannot easily break down complex tasks into individual skills or determine their frequencies. To address this, we use the observation that less frequent skills tend to have higher losses. Therefore, we minimize a weighted mean loss that emphasizes data points with higher losses. While this reweighting approach is not entirely new, its application to skill learning is unique. We pre-train a small GPT-2 model on open web text using multiple GPUs and a specific learning rate schedule. We compare the performance of our weighted loss approach against the standard mean loss. Our findings indicate that focusing on harder examples early in training yields the best results, but excessive weighting later can hinder progress due to noisy tokens. We suggest that future work should consider both the quality and frequency of skills when developing weighting schemes. Noisy tokens, which are often low frequency and low quality, complicate this process. We propose that a promising direction would be to infer skill frequencies based on their losses, although challenges remain in estimating certain parameters and applying our findings to more complex scenarios. Section Summary. In this section, we explore the phenomenon of grokking, where generalization occurs after a period of memorization, and we find that SIGD can outperform ADAM in this context, particularly in learning modular addition. We also propose a data reweighting strategy to address the challenge of learning less frequent skills by assigning higher weights to data points with greater losses, although we acknowledge the complexities involved in effectively implementing this approach. Section: Understanding of recently proposed optimizers. In this section, we explore the understanding of newly proposed optimizers. Training a large language model is both time-consuming and energy-intensive. To address this, there is increasing interest in developing more efficient optimizers that can accelerate the training of large language models, such as Lion, ADEMA Mix, Sophia, SOAP, Mars, and Muon. While these optimizers demonstrate effectiveness in certain scenarios, the reasons for their success and the conditions under which they work remain unclear. Our insights from simple test cases, like convex functions and the Rosenbrock banana function, do not fully capture the complexities of real training dynamics, such as high dimensionality and batch size effects. Therefore, we aim to create a model of moderate complexity that can represent key aspects of large language model training while remaining intuitive. We propose that the geometry model can fulfill this role. We hypothesize that the slow training dynamics of large language models stem from two main patterns in skill interaction. First, correlation or interference, where skills are interrelated due to the underparameterization of the model, leading to potential conflicts. Second, the sparsity of many skills, which means they appear infrequently in the data. A good optimizer should be sensitive to these rare skills and accumulate their effects rather than ignore them. In our geometry model, we fix the dimensionality at 10 and visualize the training dynamics of losses and skills under different conditions, varying the number of tasks and noise levels, using three optimizers: ADAM, ADEMA Mix, and Lion. ADEMA Mix maintains a slow momentum alongside a quick varying momentum, which helps it handle noise better by averaging over more steps. However, this slow momentum can introduce systematic errors in rapidly changing environments. Our findings indicate that ADEMA Mix performs better in high noise situations, as the slow momentum reduces noise variance and helps accumulate the effects of sparse skills. However, it may converge more slowly or oscillate compared to ADAM when noise is low, which is expected due to the slow momentum's tendency to overshoot. Lion, discovered through symbolic search, shows rapid initial convergence but experiences significant fluctuations later on. We observe similar behavior in our geometry model, where Lion initially converges quickly but struggles with stability as training progresses, especially under high noise conditions. We also note that different optimizers exhibit distinct personalities. Some, like ADEMA Mix, focus on mastering more frequent skills, while others, like Lion, may randomly learn skills, leading to extremes in performance. Our comparisons reveal that ADEMA mix generally achieves higher skill levels for frequently mastered skills compared to Atom, while Lion tends to either fully learn or completely fail at skills, often in a random manner. Section Summary. In this section, we explore various new optimizers designed to enhance the training efficiency of large language models, LLMs, and analyze their effectiveness under different conditions using our geometry model. We find that while optimizers like ADEMA mix can improve convergence in noisy environments by averaging skill dynamics, others like Lion exhibit rapid initial convergence but suffer from instability later, highlighting the diverse personalities of these optimizers in skill learning. Section: Implications for Task Compositionality. In this section, we reflect on our approach. We introduced a geometry model and then a simpler resource model that mimics the geometry model's behavior. While it might seem unnecessary to have the resource model since we can fully simulate the geometry model, the resource model offers advantages. First, it is generally simpler and provides better intuition. Second, there are times when the geometry model is either unavailable or too complex to construct, especially when we are more interested in overall behavior rather than intricate details. Our focus here is on modeling dependent skills, which often makes it cumbersome to specify detailed parameters. Resource models simplify the task of modeling skill dependence. We also note that dependent skills can create a domino effect. For example, if a neural network receives a bit string and needs to compute 3 sparse parities, learning becomes significantly slower as the number of bits increases. A more effective strategy for the network is to first learn the simpler tasks and then use those results to compute the more complex task. Empirically, we observe that learning the third task begins only after the first 2 tasks achieve perfect accuracy. We trained a 2-layer MLP on a substantial dataset, and we found that task 3 starts learning right after tasks 1 and 2 reach their peak performance. We propose 2 hypotheses for this observation. The first suggests that learning task 3 is independent of the other 2, while the second posits a dependency. To test the first hypothesis, we replaced the third task with one that is independent, and we found that learning was significantly delayed, indicating that the network likely relied on the first 2 tasks to compute the third. Next, we explore whether we can replicate similar skill dynamics using resource models. Working with the geometry model can be complex, so we prefer the resource model for convenience. We introduce a modification to our equations, where a specific function is large only when both inputs are small. This function behaves like a soft AND operation. The resulting dynamics align well with our experimental findings. When learning independent tasks, we can simulate skill dynamics effectively. We also note that adjusting parameters over time can lead to better agreement with experimental results, as gradients tend to increase after initial learning phases. Section Summary. In this section, we explore the utility of resource models in understanding task compositionality, particularly when geometry models are complex or unavailable. We demonstrate that dependent skills can lead to a domino effect in learning, where the completion of simpler tasks enhances the learning of more complex tasks, as evidenced by our experiments with neural networks. Section: Simulating skill dynamics with arbitrary dependence graphs. In this section, we explore how to simulate complex skill dynamics using the resource model, given the skill frequencies and the dependence graph. For a specific task, we can model its reliance on other skills with a function. For instance, if a skill only begins learning after 2 other skills are completed, we can express this relationship mathematically. Alternatively, if learning starts when either of the 2 skills is completed, we can use a different function that captures this softer condition. We can define similar functions for other types of dependencies. Our resource model demonstrates interesting dynamics that align with the specified task dependencies. For example, in one scenario, Task 3 is initiated by Task 2, which is in turn initiated by Task 1. Even though Task 1 has the lowest frequency and Task 3 the highest, the learning sequence follows 1, then 2, then 3 due to the dependent structure. Another example shows a hierarchical dependence, while a third case replaces sum and conditions with ORs, leading to unexpected dynamics where task 7 finishes learning before others, despite being dependent on them. The learning curve for task 2 also reveals fluctuations in speed, reflecting the influence of other skills on resource availability. We acknowledge that our resource model may not capture every detail of skill dynamics in real-world scenarios, but it serves as a useful reference for explaining many complex phenomena. Our ultimate aim is to tackle the inverse problem, deducing the skill dependency graph and frequencies from training dynamics, which is a challenging task. Our model takes an initial step by addressing the forward problem, using the given skill frequencies and dependency graph to predict training dynamics. Next, we discuss the implications of modularity. From our findings with the Domino model, we see that some skills take longer to learn because their frequencies are overshadowed by others. This situation arises when skills interfere with each other, sharing the same parameter space. We propose the idea of modularity, where we divide the parameter space into distinct parts, each dedicated to a specific skill, and evaluate the potential benefits of this approach. The Domino model illustrates a scenario with multiple tasks, where the frequencies of tasks create a strict learning order. When a skill is being learned, it consumes all available resources, leading to a specific learning rate. Consequently, each task requires a certain amount of time to learn, and the total time for all tasks is proportional to the number of tasks divided by the square root of the dimensions. In contrast, a modular model divides the dimensions among the tasks, allowing each skill to utilize its own dedicated resources. This results in a different effective learning rate and a reduced total learning time, indicating that modular networks can learn faster than non-modular ones. However, we note that while this speed-up is theoretically plausible, it may not be practical since we often do not know how to break down complex tasks into skills. We draw an analogy to quantum parallelism, where a quantum algorithm can significantly reduce search time. Similarly, we find that a modular network can decrease learning time by leveraging the parallelism that modularity provides. Section Summary. In this section, we demonstrate how our resource model can simulate complex skill dynamics using dependence graphs and skill frequencies, allowing us to model various learning dependencies between tasks. We also explore the advantages of modularity in learning, showing that modular networks can significantly reduce learning time compared to non-modular networks by enabling parallel learning of skills. Section: Insights from the Geometry Model. In this section, we explore insights from the geometry model. We note that a standard non-modular model randomly samples task vectors across all dimensions, while a modular model uses one-hot task vectors, localizing each task to a single parameter. We maintain the setup from section, where we have 1,000 tasks. We compare the loss scaling against the number of parameters and training steps in our figures. To highlight the advantages or disadvantages of modular models, we calculate the ratio of non-modular loss to modular loss and present these ratios in our plots. We find that modular models perform better when the number of parameters is not excessively large and during the later stages of training. Initially, modular models tend to have higher losses because non-modular networks focus on learning frequent skills, leading to a significant loss reduction. In contrast, modular networks distribute resources evenly across all skills, resulting in a synchronized learning pace. This synchronization becomes beneficial in later training stages when non-modular models struggle with less frequent skills. In our real MLP experiments, we set a task to predict the squared values of two real numbers. We create a hierarchy in the training data by making one of the inputs sparse, where it is 0 most of the time. We train a specific MLP architecture using the Atom optimizer and monitor the mean squared error loss. We observe that the sparse input is learned more slowly, confirming our expectations. Notably, the time to learn the second task appears to be at least double that of the first task, aligning with the domino effect. When we understand the modular structure of the tasks, we can separate the MLP into two subnetworks without cross-connections, effectively training them independently. Our results show that the learning time for the second task is similar to that of the first, although it may have a slightly longer tail due to the sparsity of the input. Modular neural networks have gained renewed interest due to their success in language modeling, particularly in mixture of expert models. Their advantages are often linked to task compositionality and module reuse. Our analysis highlights another benefit: faster training. However, determining how to partition networks into modules remains a challenge. Recent work on gradient routing, which applies data-dependent masks during backpropagation, shows promise but has yet to be applied to language models. In the realm of learning theory, understanding the success or failure of neural networks is crucial. Mainstream theories, such as pack learning and methods based on statistical physics, have partially succeeded in explaining static properties of neural networks. However, dynamic properties require more advanced theories. Singular learning theory shows potential for describing training dynamics, particularly phase transitions, but its computational aspects can be complex. While classic theories have solid foundations, they sometimes fall short in practical applications. They may oversimplify data modeling or fail to capture interactions between parameters. In practice, the collective behavior of parameters is what matters, as seen in the emergence of semantic meanings in certain directions of the parameter space. We also discuss task arithmetic, where task vectors can be modified through arithmetic operations, influencing model behavior. Our geometry model relies on this structure and assumes a condition for weight disentanglement. We address the concept of phase transitions in neural networks, noting that complex systems, including neural networks, can exhibit intricate phase diagrams. These transitions can occur during training or when control parameters change. Initialization scales are crucial in determining training stability, and dynamics are most effective at the edge of chaos. Neural scaling laws describe how model performance improves as resources increase, and understanding their origin has led to various theories. Researchers are exploring ways to surpass current scaling laws through data pruning and new architectures. Finally, we note the emergence of new optimizers that outperform traditional ones like ADAM, particularly in language model pre-training. While these new methods show promise, the reasons for their effectiveness remain unclear. Our geometry model serves as a useful testbed for evaluating optimizers, balancing simplicity with the complexity needed to reflect real-world features.